Okay, so welcome everybody to our bi-weekly N3AS Seminar. So today we have Djuna Croon to talk about black hole archaeology with gravitational waves. So Djuna is currently junior faculty at IPPP in Durham in the UK. And before she was actually in the US, she was postdoc at Dartmouth College and also in Canada at Triumph. And yeah, so please, Djuna, go ahead.
Yeah, thank you for having me. As I was saying to Lucas earlier, I am actually just recovering from COVID. So yeah, I'm good now, but like if I'm coughing a bit more or scraping my throat a bit more, that's what's going on, or like drinking a bit more. Don't worry, I'll be fine. Okay, yeah, I'm happy to talk to you about this topic that I've been studying for a little bit of time now. And yeah, I'm a particle physicist by training, but I'm very interested in astrophysics and especially stellar astrophysics and gravitational waves now. And I'll tell you all about it. So I'd like to start with this plot here with temperature and density, just to put like things a little bit in some context, if you will. And then I'll kind of explain the link to particle physics in stars as well. So you see here these like in astrophysical units, like temperature in Kelvin and density in gram per centimeter cubed. And let's put some objects that we know, on this plot. So the core of our sun is about 10 to the 7 kelvins and like it has a density of about 100 grams per centimeter cubed. So that's very dense and very hot, but still not hot enough to be anywhere but in the left-hand corner of this plot. Then I put some other sort of stages in stellar evolution in here. There's this kind of like generally kind of as stars evolve, they become hotter and denser in their core. So all the way until this kind of tip of the red giant branch here. Then what happens to stars in their evolution, of course, depends on their mass. Lighter stars like our sun eventually become white dwarfs. They only evolve through hydrogen burning. And then they actually stop their nuclear burning and they just cool down and have this kind of density of like the degeneracy of electrons. But heavier stars than our sun might actually evolve through progressive burning stages, which they burn through like progressively heavier nuclear elements sort of on the horizontal branch. And you've got this kind of post-main sequence evolution generally going on kind of over here, where you first burn through helium and then carbon and then heavier elements, depending on the mass of the star, of course. Now, very heavy stars actually become neutron stars, and I just, these are kind of interesting objects as well, of course, for a particle physicist. I put this here on the star. These have kind of the degeneracy, they have the kind of the densities that are related to the degeneracy of neutrons. And they're first very, very hot, so hot actually that maybe they can even be an order of magnitude than what I put, hotter than what I put on the plots here. And then, but they cool down very quickly. And then within a few years, they actually kind of cool down all the way, just because there's no, thermonuclear burning in their core anymore. Now, for particle physicists, what's very interesting is how you kind of actually translate between Kelvin and keV. And I've just sort of given you this translation here because this actually relates to the type of particle physics that can happen in the course of these stars, because this is kind of the temperature obviously translates to the energy that a typical photon can have. And so therefore the typical particles that you can hope to produce in your course of stars. And so that type of game has been played, that's not something that I've invented. It's been played for many, many years. But that's kind of roughly the picture that you should have in mind, and kind of the object that you want to study and the particle masses that you're sensitive to are kind of directly related by these temperatures. Okay, so then roughly the picture is like, why would you do particle physics in stars? If I have kind of this type of plane that particle physicists love with like interaction on the y-axis and particle mass on the x-axis, the type of particle physics that we can do on Earth is like where you have a relatively like large interaction strengths, and you can probe up into obviously the typical energies that you have in colliders. And all the particles of the standard model that we have discovered on Earth sits here somewhere here in this type of range, where stars can help. Like obviously you've seen that like on this plot here, these masses here, KeV masses, this is actually nowhere near what the LHC can, for example, probe. So you're typically not going as high up in energy, but what helps is that you're typically sensitive to much smaller couplings, just because you have a large core of a star and not a small, like, interaction in the beam pipe. So, so here you have this kind of range in which stars can help, and whatever happens over here, that would be a shame if new physics happens all the way over here. So it's just kind of a rough picture. Now, what am I interested in today? Well, what's really cool is that now we also have these access to binary mergers. And what binary mergers and gravitational waves give us access to for the first time is kind of this kind of picture of like what black holes and neutron stars, these stellar remnants, what types of what their masses can be and their properties can be. So what I'm showing you here is kind of all the binary mergers that have been discovered by the LIGO Virgo GAGRA collaboration in their first to their third observation runs. So it's kind of an artist impression here. The x-axis doesn't necessarily mean anything. The y-axis is the masses in solar masses. And so you see here, like from two progenitors to emerged objects. And so this is actually, really kind of, like amazing how many sort of, how much access we have to black holes via gravitational waves. And so this is only with 3 observation runs, and there will be 5 in total. And the detector is getting more and more sensitive, of course, between updates as well. Right. You see here, that's like, there's here, these orange dots are what are likely to be neutron stars, and these blue dots are what are likely to be black holes. And there's, of course, also a few objects there, a little bit more mysterious over here. Here, these other objects, these red objects here and these green objects here are like the electromagnetic detections of black holes and neutron stars. So for those detections, you need to have some other type of signal, like, for example, the black hole needs to be in a binary with something that does radiate electromagnetic in the electromagnetic spectrum. And so the real kind of win here is that for these binary black hole mergers, you don't actually need an EM signal to observe them. And so you're not like dependent on something happening relatively close by and in a binary with like something that radiates in the electromagnetic spectrum. Okay, and so now that we have this access actually to this type of, to the populations of black holes, really, we can actually start to think about, what these populations might look like from stellar structure theory. And so there's actually 2 things that are quite interesting, and they're both called mass cap. And so I put them here on the plot. So one of the things that is kind of this hypothesized mass gap, which may or may not exist, is between like the heaviest neutron star and the lightest black hole. Whether or not this exists is not a very firm prediction as far as I understand. It's just that the heaviest neutron star that's been observed sits somewhere at about 2.3 solar masses. And the lightest black hole, like that's been observed through AM radiation, sits a bit above it. So there might be a mass gap here. With black holes, with binary black holes, and the LIGO observations, it's not actually clear whether there is a mass gap. And there's definitely a few of these kind of like objects in between that look like they have masses which would sit in where you could predict the mass gap to be. And the nice thing is also that because typically these binary mergers here with objects here are in have a relatively high mass ratio, you actually have access to like multiple, like quite enough of the inspiral waveform to actually get a good like non-degenerate mass prediction here. So these don't have the huge error bars that some of these measurements do. but I'm digressing a little bit because this is actually not the topic of this talk. What I'm going to talk about is this hypothesized mass gap over here, which is, I would say, like a relatively robust prediction of stellar structure theory and stellar evolution. Where exactly it lies is more of a question mark, but that it exists for black holes that are the final states of heavy stars is a robust prediction, only because it relies only on a few different ingredients, if you will. And that's what I'm going to talk about now. So that's the topic of this talk. Good. So again, here's this plot again, just to point you at where I'm going to look at. I'm going to zoom in here on this post-May sequence evolution. And here's that same plane, but then just a little bit like a little bit differently, just zoomed in, if you will, with here this core temperature and here this like core density. And what I'm showing you is the late evolution of a few heavy stars, which is simulated with this stellar evolution called MESA. So you see here that like these stars that we started off around at the onset of helium burning, at helium ignition, evolve, like slowly burn through helium, and they evolve like to hotter and denser cores, as I said before. So what first happens is like helium burning, and so the two nuclear reactions that are, you know, the main reactions that power the star, if you will, in this stage of the evolution are this like triple alpha process where you've got 3 alpha particles, helium particles. First, you get a beryllium core atom, and then capture another alpha particle and become a carbon. So this is an exothermic reaction which powers the star, and another exothermic reaction that powers the star is this other process where this carbon atom that I formed captures another alpha particle and then becomes an oxygen. And so these are both very important processes, and especially this one is very important for reasons that I'll come back to in a moment. Then, as eventually, obviously, you run out of helium, and you start to like collapse a little bit, and then ignite carbon, and so you have these other nuclear reactions taking place in these stages of the evolution. Sorry. And you see here that like these tracks are like, they seem like roughly in parallel, these larger stars, these heavier stars, at the same temperature, they're slightly less dense, if you will, or equivalently, you could say at the same density, slightly hotter. But the real difference is starting to happen here, and actually these tracks are not even kind of monotonically going upward anymore. And why that is because there's something else that I haven't told you about this plane, and that's that there is this kind of big region here, which I've labeled here as unstable, in which like the adiabatic parameter, first adiabatic parameter is less than 4/3, which means that the star is unstable. So what's happening here? What's happening is that like, so these are actually very high temperatures, right? And I don't have here these masses anymore of particles, but if I did, you could have noted that actually these temperatures are kind of actually not that different from the mass of an electron. And it's still a bit lower than the mass of an electron, but not that different. So it means that like these high temperatures mean that the photons in the star have enough energy to produce electron-positron pairs. And so that can happen, but also these electron-positron pairs are still, the mass of the electron is still smaller than the temperature, meaning that these are produced non-relativistically, and so they're not produced as radiation. And so what is happening is like, I'm actually converting radiation into something non-relativistic, and so something that contributes to pressure to something that does not. And so I'm actually destabilizing the star. So that happens in this triangle. Why does this triangle have this shape then? It's because above these at higher temperatures, these electron-positron pairs are actually formed relativistically, so they also behave like radiation and also contribute to the pressure of the star. Below here in this region, this process is just 2 Boltzmann suppressed, And here on the right, there's this ionic pressure. It's another source of pressure in the star, which actually is more important. So that's why this region has this particular shape. And you can calculate this like semi-analytically as we did, but you'll find also that this roughly corresponds to the region that like these tracks become unstable, or the stars that you simulate in these tracks starts a core collapse. Now then what happens in core collapse of these stars, that's actually kind of pretty destructive, especially for these heavier stars, because I actually had formed some oxygen, as I told you before, especially here in this reaction with helium. There's this process here forming oxygen, and oxygen has an explosive burning cycle. So I actually can set in motion this chain reaction of catastrophic events for the star. So let's go through that in a little bit of detail. In a nutshell, what happens is like, okay, it starts with a blue supergiant star. And what happens is that like the core of this star becomes so hot that like I produce non-relativistic E plus E minus pairs in the stellar plasma. And these destabilize the core of the star, triggering premature core collapse. But then like the explosive burning of oxygen, which was the burning product of helium, like gets ignited. And then one of three things might happen. And what happens actually depends on the mass of the star. So these very, very heavy stars, actually, like you can think about a star, an initial stellar mass of like 200 solar masses or something like that. These very heavy stars. There's actually this photodisintegration instability, which I'll come back to in a moment, a little bit more, but that triggers this immediate black hole collapse. And so this whole process gets shortcuts. You still have this like explosive oxygen burning, but what actually wins is the photodisintegration instability, and immediately this thing collapses into a black hole. For slightly less heavy stars, but of course still very, very heavy stars, this explosive oxygen burning is actually so powerful that it like releases so much energy that it imbibes all of the material in the star. So basically all the material in the star gets escape velocity, and that's called a pulsational pair instability supernova, PISN, pair instability supernova. So I end up with nothing at all, actually. So all of this material gets blasted out, and I leave no remnant of the star. And then some of these like lighter stars, but still obviously talking about very heavy stars compared to the sun. You actually this explosive oxygen burning triggers like sort of some material to be blown out, but not all of it's ejected. And so the star can actually undergo this like cooling again, and even go through the cycle several times. And so that's called a pulsational pair instability supernova. So in the end of the day, I might end up with a remnant because like, eventually like it settles into some sort of thermonuclear stability and just undergoes like a normal evolution into a core collapse. But that remnant might be much lighter than I would have expected otherwise, because I've blown all this material out at this step. So what does that mean? If I just like kind of do this type of simulation for stars of many, many different initial masses, as I did here, then, and I forgot here to put what type of metallicity this is, but I think this is relatively high metallicity. I think this is like a tenth of the solar metallicity. Yeah, I have to do this for many, many different initial stellar masses, and I simulate this and I figure out what the final black hole mass is. Here on the left-hand side of this plot, you see that that actually kind of tracks this like dashed line well, and this dashed line is the mass of the star at helium depletion, which actually corresponds to the initial stellar mass minus the stellar winds. And so that's actually kind of like a very good prediction here for these lighter stars. But eventually you see that I start to curve over, and what's happening here is this pulsational pair instability supernova. And so like these stars over here have undergone pulsations, which blast some of the material out, and therefore the final remnant is actually lighter than you would have otherwise expected. And eventually I end up with no black holes at all. And so there's this whole range of like initial stellar masses here where there's no black holes formed. And if I would have continued this plot much further to the right, at some point I would have picked them up. And later in the talk, you'll see plots where I do this, but I haven't done this for this description here. Right. So this is kind of what I just said. Whether or not they undergo, whether or not like E plus E minus pair production is important, and the subsequent instability is triggered. So this has immediate implications for black holes, obviously, because if I just like draw the asymptote of this line here, see there's this whole range of black hole masses that are just that I actually don't find, and that's like the if I would have continued this plot further to the right, black holes that I finally end up picking up again are just roughly on this like line again, if you will. So there's this whole range of like black holes that are just not formed as the remnant of stars. So yeah. Let me just, yeah.
I just wanted to ask that the red dots, are they meant to be particular observed quantities? Because I wonder why there's nothing plotted between 20 and below 20 M Sol. Or is this meant to be indicative without being precise?
This is the result of simulation. So this is a simulation in which there's an initial stellar mass here, like where I simulated these stars, and then the final black hole mass that you would have predicted in red. So there's nothing, but the reason there's nothing below here is just because I haven't simulated light enough stars.
So you would expect some kind of fill-in, but you don't know.
Yeah, I mean, if I continue, I mean, I think later on in plot, like it's just that for this demonstration, it would look kind of boring because it would just be on this line. But typically we simulate stars from about 20 solar masses and upwards, and you would just see this line continue.
It's fine. I was thinking, to my mind, given your earlier Aaron Geller slide, it is the trend to zero at high MN, which is very interesting, whether or not you fill in all the way to zero. I just was curious. Thanks so much.
Yeah, right. So yeah, for that type of simulation, so once you get to these like much lighter stars, it becomes a little bit harder to simulate. Like we typically simulate from about 20 solar masses because we're interested in this heavier variability mass gap. But you're right, it's also very interesting to look at these lighter stars. Yeah, just I'm talking mostly about those.
Thank you.
But, yeah. From this plot, like you can't deduce anything about what happens to this lower mass gap. So yeah, no black holes are formed here. And just to remind you, this prediction, so that, like this doesn't actually rely yet on any physics beyond the standard model. Actually relies only on the mass of the electron and the fact that electron-positron pairs can be formed in the star, and on the fact that oxygen has an explosive burning cycle. So two like relatively robust things. Where exactly this happens, of course, there is some like, dependence on the parameters in the star, like metallicity, as I just said. But the fact that there is there's this region of black hole masses that can't be formed is a robust prediction, which only depends on two elements, really. Okay. I just wanted to talk very quickly also a little bit about this like photodisintegration instability. So what really happens there is just there's this kind of really rapid absorption of high energy photons, which then just means that actually you reduce this first adiabatic parameter even more. So I was already like my core was already collapsing, and then this very rapid absorption of photons just leads to even more contraction. And so instead of like actually having this contraction and then this explosion from oxygen burning, the oxygen burning can, for these very high mass stars, no longer keep up with this contraction due to photodisintegration. And actually then you shortcut this whole process and you immediately collapse into a black hole. Just to understand this upper end of the mass gap. Okay, good. So now I've kind of introduced like what the upper black hole mass gap is. I'm going to talk a little bit about what might happen with new particle physics, and then I'm going to talk a little bit about how you might detect it. So just kind of very naively, like new particles can do a lot of things to stars. The very easiest thing to study is, of course, where particles are produced in the star and just like free stream out or just fly out. So like just like neutrinos are very weakly interacting, they're produced and then they just fly out and they just act as a loss channel for the stars. But they can also kind of get trapped in the star and then affect all the processes in the stars. So it affects the equation of state, but it also affects like energy transport within the star. And yeah, that's kind of another type of scenario that you might study. So some people have studied also like, actually collecting new particles in a star and then annihilating in the core, or what you might think of is so dark matter, for example, even maybe seeding a star or like being already present in some way and leading to extra kind of annihilation, powering the star. And what might happen, and sorry, this should have said the star evolves differently, but that fell off because my fonts or something. Or what might happen is like, rates in the star are modified. So today what I'm going to focus on mostly is like only one of these. So this more trap scenario. Besides new particles, but you can also study, and in particular relation to the black hole mass gap, is nuclear astrophysics. So actually this rate is like 12C16O rate where you produce oxygen. It's obviously kind of like very important here. And it's important for other stellar astrophysics processes too. So you can turn this question on its head and say like, you could study actually what this rate is using nuclear astrophysics. So these people have proposed. And like, what you could also say is like the black hole mass gap is actually a test of like Newton's constant in the star, because obviously Newton's constant depends on how strong gravity, like determines how strong gravity is. And so lighter stars start to behave like heavier stars if I increase this and vice versa. So that actually changes things as well. Today, what I'm going to talk about is like slightly heavier particles, which are quite relatively strongly coupled. And I see that there's a question in the chat here. The question is rotation. Yeah, that's a good question. Rotation might affect this as well. Like we haven't really studied it in too much detail. I think typically what rotation has done from memory from other papers is, or spin, if you will, of the star, like rotation. Rotation of the star would, I think, like shift the black hole mass gap upwards, if I remember correctly. But it's not something we've studied yet. So if you have another question, maybe you could unmute yourself, because I don't actually monitor the chat. I can't really see the chat unless I just happen to see it.
Thank you. I'm unmuting myself. So yeah, I mean, rotation is an issue in the evolution of these stars, because nothing else, it gives you a kind of a one-dimensional centrifugal contribution that is acting against gravitation. But it also brings up the issue of how the burning goes. So if I can't remember how these papers went, but if you look at the papers by Hager and Woosley and the early papers, for example, so where they were trying to produce explosions, the angular momentum seemed to help.
Right. Okay. Seemed to help as in like it would increase the effect of explosions, or? Correct.
So I think I'm saying that it's easier to explode the star with rotation. And an explosion is, as you say, complete disruption, so no remnant.
Right. Yeah, right. I need to look into this a little bit more. It's definitely also on my planning. But yeah, everything I'm saying now, there's no rotation, but it's indeed like and also another effect. Yeah. So yeah, I guess the inspiration of what these new particles that I'm talking about now are these particles that are like quite relatively strongly coupled and also relatively heavy. So you could think of axions that are in this cosmological triangle. Why is this called the cosmological triangle? Because there's constraints here from astrophysics and from lab-based experiments. but no constraints in this triangle. The only constraints that you could put in here depend on your cosmology. So as like axions in this type of triangle are relatively strongly coupled and relatively heavy, and that means they actually affect the star differently. Like, but you can't just assume that these particles are produced in the star and actually just escape like neutrinos do. Therefore, they're too heavy and too strongly coupled. So one thing that you might expect then is if these couplings are large enough that you actually even start to have like an equilibration process, and that like the kind of timescale of equilibration of these particles is actually comparable or shorter compared to the evolution of the star. And so what you might expect then is like, you had this kind of instability region here. This is very schematically the instability region due to peri-instability supernovae, and then kind of like stellar evolution was kind of roughly in this gray bands. This additional instability caused from the which comes from the production of these new particles. And so what we call this is like an AISN, like an axion instability supernova. So like if an axion has the same mass as an electron, this kind of region can be larger, both because I'm adding to an instability that was already there, and also because this type of axion has a slightly different statistics because it's a boson. Okay, so we wanted to kind of figure out, like, if this is kind of, if something actually happens to the evolution of the star, if like these axions are produced. But that's a little bit harder to actually figure out than just doing this type of naive calculation. And so what you actually want to do is like actually update the stellar equation of states and actually calculate the axionic contributions to all these different quantities that your simulation evolves. And so, yeah, that's what we did. But of course, doing this, we had to also assume that like these particles were actually present in the star. And so the check that we did is like checking that like the rate of production of these particles was larger than the typical rate of evolution. And the rate of evolution, we took like the T dot over T of our stellar evolution program. So we just monitored at every step, like how quickly the temperature evolved, if you will, and then compared it to the production rate of these axions. And I'm putting here on the plots two different ways of producing axions. One is the Primakov process, and one of them is coalescence, the percoalescence process. And these are both here, kind of up here. And you see that, like, especially here before this, like, I put here PI as N, but I could have put here AI as N. Before the explosion, these rates are like safely much larger than the kind of typical evolution, temperature evolution rates of the star, if you will. And so that kind of motivates our assumption for calculating all these quantities in our stellar evolution software or simulation. I should say, like, we actually did write a simulation package, which I should have linked here but didn't, to sort of where we kind of like show and explain how to kind of update these quantities in Mesa to do this type of simulation, and with a manual and everything. It's linked in our paper. Okay, so I just want to show you like the difference in evolution. Just kind of like show you for a typical 50 solar mass star what happens. Here I've kind of colored this evolution, based on the kind of model number, which is not quite the time, but it's kind of a proxy for the time, just because the star doesn't update like at equidistant time steps, if you will. But yeah, I'm kind of showing you here like what happens. Obviously you've got this like density evolution up until the point that you had this explosion. You see here also like the kind of mass fraction of the core of the star what happens. And so like the explosion actually happens during like carbon burning, so where you have like quite a lot of carbon, and also silicon is on the rise because you're burning carbon. Yeah. So this is just for one star. Just kind of wanted to show you the resulting black holes in these simulations with this new instability. So this is like for the standard model. You would see this plot is slightly different than the plot I had before. And the reason is that like, I assumed a different metallicity. The metallicity on the plot that where I explained this with was rather high. It was like a fraction of 10 of the solar metallicity. Here, what I'm showing you, this is a metallicity of 10 to the minus 5, which is like the type of metallicities that you would see for these very, very early, very heavy population 3 stars, for example. And you see here that like, you know, the actual very big, like the kind of qualitative behavior of these like things is similar, but the numbers are actually quite different. And you see here that this instability actually starts to kick in at much lighter masses when you have this new axionic particle produced as well, as you would expect, because your range of the instability in your plots increased. Another kind of aspect of this is actually also not super surprising if you think about it, but because you actually lighter stars now encounter the instability, you also actually get kind of a different in luminosity that you have. And so I'm showing you here like two different results for simulations with this extra particle, this AISN results, and compared with like a PISN result of 70 solar masses. And you see that like the luminosity is like quite a bit higher for those. Okay, the other thing is it's not just actually that this affects like this lower edge of the mass gap. Actually, if you continue your simulations all the way forth to these like very heavy stars, photodisintegration kicks in earlier too. And so it's actually not that you even really widen the mass gap, if you will. If anything, it's actually slightly decreased the width of the mass gap, but it's mostly just kind of shifted down, and interestingly. And that's actually also kind of interesting, just because these like black holes, these very heavy black holes, very hard to observe also, but with like the current ground-based interferometer experiments. But these lighter ones, these actually start to become in the range that they're easier to observe. Good. Okay, so then in the last part of this talk, I just wanted to talk a little bit about data, because like this is of course all well and good, but you know, it's kind of I want to kind of link back to gravitational waves and why this is actually something that I think you can observe, and you can actually do better and better at in the next few years. So I started with this kind of catalog here, this kind of artist representation, if you will, like you know, of all these different black holes. Of course, what I can do is just kind of actually look at the distribution of masses in this plane, and then you get something like this. Might not tell you too much yet. But so this is like from GWTC3, which is all the data that's currently available from the first to the third observation runs. And so you look at masses. Of course, you can also look at other things. Masses are not the only things that are parameters that are estimated from these gravitational waveforms. You've also got spin alignment, eccentricity, redshift. All these things can tell you a little bit more about black holes, and also kind of the populations of black holes that you have here and their origins. Now, what do we predict? Well, we predict something like this, right? All this plot that I've been showing you again and again is just like where you have a stellar mass and then the predicted black hole mass, and roughly the shape would look something like this. So we predict black hole masses from stellar masses through these simulations. That of course, that prediction can then be changed by new particles. So I'm just like showing you some like slightly other, like my own artist representation of another type of curve that you could see. But you know, like qualitatively, the behavior would be quite similar. So then how can we use the data to test that? Well, it was actually quite nice, and it was already observed like by Talbot and Train some time ago, not that long ago actually, but is that like for this like whole wide range in stellar masses here, you see, because of this turnover type of behavior, you actually have like a small range of black hole masses that's produced. And if you calculate it, it's actually kind of, there's this like black hole mass for black hole range for which this like the actual this range actually becomes very, very narrow for like you know, a relatively wide range of stellar masses. And so if you actually calculate this, you have to assume some initial stellar mass function, of course. And I guess it's a relatively, you know, it's a relatively good assumption that like initial mass function is a power law. At least there's no real arguments that I know that it would be very different from a power law. And then if you do this calculation, there's actually this kind of pileup that happens here due to this type of effect. Even like theoretically, it would actually kind of formally would kind of diverge if I would this type of calculation. Of course, that's never really what you actually see in nature, but there's this kind of like spike that happens. So there's this initial fall off, which is just set by the initial mass function, and then there's this like pileup here. And this pileup happens right around the lower edge of the black hole mass gap. And so that's actually a feature that you can then look for. So it's not just that you don't expect black holes anymore above a certain range. It's actually that you also have this kind of feature pointing it out to you. So that's quite nice. And it's also nice because there's, of course, there's always ways, even astrophysically, of populating this range through prior mergers or something. Now, we came up with a nice kind of way of fitting stellar evolution results. We have kind of a proposal for what this actually might look like, you know, based on parameters, like with like where the shape is kind of giving you this type of narrower spike or wider spike. And so that's actually something that you can then directly fit to the LIGO data. So first, just let me show you like different types of scenarios that we've all tested. So different types of scenarios that we've like, you know, simulated here, and then the corresponding like function, like the corresponding like black hole mass function in this parameterization as well. And you see this all like pretty good fits, and like the, you know, the shape of this function changes a little bit, and also where this peak occurs. And for the particular, you know, stuff that I've been talking about so far, for this AISN, where I produce an axion in the star, you have this type of simulation I should show you here for two different metallicities. You see there's a slightly different result here, and you also get like a black hole mass function like here. So you see here, there's like, you know, the metallicity matters. So this is like 3 orders of magnitude in metallicity. So it does actually matter. The metallicity changes like where this black hole mass gap occurs, but still like the difference with the standard model is much more than this. So yeah, anyways, as I was saying, like, you know, it's not like this is not the full story, of course, because you can actually populate this mass gap differently, because of course you could have some sort of dynamical merger scenario in which prior mergers actually lead to heavier black holes which populate the mass gap. So this is like a first generation, and the first generation we would expect to have this type of mass function, but second generations would look something like this, where I calculated this just like using the assumption that like binary information doesn't care about mass. Which, you know, may or may not be the case, but like the details, you know, like are not necessarily that relevant. There would just be a second generation. There could be a second generation population And exactly how it's normalized isn't super clear, but this distribution would inherit from this first generation distribution, and there would be a discontinuity. So there's actually, there would be, if there's different population, there should be a discontinuity in the mass function. So yeah, there's one way to model it, I think. So what we did in our first paper where we analyzed like gravitational wave data is just model this by sort of a flat function and a fall off here. So yeah, these are results from this like first paper. We're actually working on an update of this. So this is actually, apologies, but not with all of the data so far. It's up from observation runs 1, 2, and N3A. So the third observation run splits into 2 halves. This is only the first half. Still, like, you know, a good number of mergers. And so we kind of compared the results of like our model based on stellar evolution simulations to the most successful model of the LIGO Virgo and GAGRA collaboration, which was the power law and peak model. And you see here, there's a bit of a difference, especially where kind of the peak occurs. And sort of our preferred peak with like relatively large error bars with this small data sets is actually much higher than like the peak here that's preferred here. So actually the conclusions are quite different, but actually in this type of like what's nice about our mass function is that's quite transparent how to interpret these different mass. There's actually only 2 dimensional parameters in this model. One is like where the black hole mass gap would be, and one is where this like kind of minimal black hole mass would be, which relates to this lower mass gap. So yeah, we did this kind of like with this without this one event, because that event is actually kind of a bit of an outlier, at least in this prior data sets. But I think the evidence is actually much better for this with this event, and I think it's kind of since there's other events that are like this too, so we should consider all the data. So now we're actually updating this and also taking into account spin in a kind of an updated version with the rest of the data sets. So yeah, so that's what I wanted to sort of talk about. So I should say, like, you know, there's kind of, you see there's like, so big error bars on this yet, but this is with only a data set which includes roughly half of the data we have so far, which is about 50. Well, this was about 30 mergers. Now we have about 50 mergers, but after the next 2 observation runs, that actually would be hundreds of them. And so actually you start to actually do much better and actually get a relatively good prediction like of what the black hole mass gap, like edge of the black hole mass gap, where it would be. And I actually am very hopeful that we could actually pin this down where this peak is, and then that will help us actually look at stellar evolution and what happens in stars, and perhaps if there's any new processes in there that we didn't expect, and otherwise like kind of look at just stellar structure theory as we know it, and see how robust its predictions are. So good. Yeah, that's already brings me to my conclusion. Well in time for some questions. So that's good news. I mean, I really am interested in gravitational waves. I think it's fascinating that we can study black hole populations now. And there's all these other questions that all these other astrophysical things that you now have access to using gravitational waves. It's just an entirely new probe of studying stellar astrophysics and also particle physics. So I've talked about periinstability supernovae. That's kind of a very interesting type of event leading to an unpopulated space in the stellar graveyards, not necessarily an unpopulated space in black hole populations, but a definitely unpopulated space in the stellar graveyards. And the black hole mass gap is like is a really new probe of like particle physics and also nuclear physics and the physics that happens in the stars. And eventually, I think we can actually draw a conclusion from black hole population studies allowed by gravitational wave data, and we can do the black hole archaeology to figure out what happened in the stars preceding these black holes. So thanks, and yeah, I'll stop here and I'll answer any questions that you have.
So thank you very much, Djuna, for a really nice talk. So do we have any questions now?
Yeah, I should say also, I mean, if you don't want to ask me questions now, you could also send me an email later. I'm always happy with that too.
So maybe let me ask, so how distinct would the effects of new physics, say these axions, be, for instance, like or the other way around, how degenerate they are compared to other nuclear physics effects? So I think it's at one slide. I think you
yeah, I have
like,
this slide.
Yeah.
Yeah. So, oh, this is actually, sorry, this is not the one, like, so I think something went wrong with my fonts here. But yeah, anyways, this is a study was done by other people in 2019. And you see here all these different effects that you could take into account. One thing I want to say, you see here that the rates, especially this rate, this carbon oxygen rate, obviously is very important because oxygen is like the whole culprit. So this was with like a kind of old nuclear rate, because that was the rate that was in the StarLib catalog. If you use an updated rate, there's actually this prediction moves up a little bit, central value, and the error bars shrink also by a bit. So yeah, anyways, like, you know, these are kind of the error bars. So there's like definitely some degeneracies. There's like the metallicity and the rates are the most important, and then stellar winds. But you don't actually see anything that moves this below, you know, like for these axion models, we actually found like about 35 solar masses. So there's still, you know, even if there's degeneracy with other effects, some of these like new physics effects are so large that like, you know, that still seems unexpected, like given these type of error bars. Does that make sense? Yeah. And I need to fix this slide.
Okay, thank you. Are there any other questions?
Yeah.
Oh yeah, George.
Yeah, thank you for a nice talk. It's very, very good. So the reason I'm concerned about rotation rates is basically the onset of burning once the instability sets in. So once the instability sets in, which is going to be, as you point out, inevitable at some point, because the adiabatic index falls, you know, quite low because of the shift in the electromagnetic equilibrium into pairs. So and absolutely, like you say, it's interesting. You're in this regime where the electrons and positrons are actually kind of non-relativistic. So you're not really trading one relativistic pressure producing species for another. But then once the instability sets in, it's a question of the thing starts to fall inward, building up kinetic energy. And the more it builds up kinetic energy, the larger the burden on nuclear burning to turn that around. So what rotation does is provide a little bit of a spring, a little bit of a place to store some energy. So it kind of alleviates the burden on nuclear burning a bit. You know, it's still, I don't know whether it would be a very big effect or not, but I know this from looking at it, that from looking at the instability in more massive stars, which is the GR instability, which is similar in many ways. So there it's this race between the buildup of infall kinetic energy and nuclear burning, adding, thermal energy.
Mm-hmm.
But then also there's another issue, which I was going to ask you about, which is that, if the temperature gets high enough, and it probably doesn't in explosive carbon burning and oxygen burning, but if the temperature gets high enough, then ordinary standard model neutrino losses become quite significant.
Mm-hmm.
You're around the temperature where that begins to become important.
Right. I mean, neutrino losses are
a lot of electron-positron pairs, and so the neutrino emissivity is going like 9 powers of temperature. So if you add additional cooling, it probably seals the deal, shall we say. You're not going to get an explosion. So.
Right. Yeah. So I didn't actually show you this, but like we also looked at cooling. Maybe you see it in some backup slides. I don't know. I should have looked at what I picked with me. I don't think I took this with me. So anyways, we did actually look at like other kind of BSM effects with like additional cooling, if you will, in previous works, and then compared it with neutrino losses. So here I'm like showing you, for example, here where like this extra loss over the neutrino loss is like 1. That's this like dashed like orange line here. So yeah, indeed, like for these temperatures here, like carbon burning, it's around 10 to the 9 Kelvin. Like neutrino losses are also very important. Neutrino losses are taken into account in these simulations though. Yeah, and then you can put on top of that, which is nothing that I talked about so far, but in top of that, you can put on other particle losses. I talked about like where this new particle is actually not escaping and just like staying in the star. Yeah, but rotation is something that I definitely need to look into a little bit more. Yeah, you're right. It's like, and actually how to simulate that as well.
Well, it's only going to be important, I suspect, if at all, on the margins, right? Near this limit of where you get an explosion or where you get a black hole remnant.
Yeah. No, definitely. Like, yeah. Thanks for the explanation as well. Like, that's definitely something to explore a bit more.
Thank you.
Yeah, thank you.
Okay. Thank you. Any other questions? Yeah, I don't see any more hands. So yeah, let me thank the speaker again. Thank you, Djuna.
Yeah, thank you for having me. Yeah.
I'll stop the recording.